Hello, everyone. My name is Dr. Natalie Hobson, and in this video, we're going to go over an introduction to confidence intervals together. So in this section, in this video, and in these notes, you'll look at how to use a sample statistic. So reminder, that's, for example, like a sample mean or a sample proportion to make inferences or infer information about the true population parameter. So that means the mean or proportion about the population itself. We won't be able to know anything for sure about the population, but we can find a range of values that are reasonable for our population parameter. So this range of values, that is going to be our confidence interval. And before getting into the details of a definition of a confidence interval, let's just say a few words about what I mean by range of values. So you've certainly seen ranges of values elsewhere in your life. For example, if you are interested in the range of temperature values on a given day, you are given a low temperature and a high temperature. So for example, our temperatures for that day could range between 37 degrees Fahrenheit to 48 degrees Fahrenheit. Maybe we're still in the winter here. So this range of values from 37 to 48 degrees Fahrenheit is what I'm considering when I say a range of values. Often we write a range using interval notation like this. So 37 degrees, comma, 48 degrees. So that notation means all of the values from 37 to 48 degrees. So that interval is a range of values. Okay, let's get into it a little more. So let's look at the definition. A confidence interval is a range of values determined from a sample statistic that captures the true population parameter with a specified probability. So we're going to go ahead and unpack that definition now, and specifically look at how confidence intervals are created. So in general, and in statistics, parameters of a population again, examples here meaning mean, the proportion, those are examples of parameters, are often used to estimate, or often are rather estimated based on a sample. And that's exactly what we do when we create a confidence interval. So let's look at that a little bit visually. So let's suppose we're looking at some population data. So for example, let's say heights. So I'm just going to make a number line here of heights. And I'll label my number line. So maybe here we'll be at 4 feet. And this will be in all feet. So I'll just write that here so I don't have to repeat. So 4, 5, 6, 7 would be way up here, etc. Okay. So what I'm going to do is I'm going to plot my population on this number line. So I'm just going to place a dot for each person in my population. So maybe our population is everyone at our school, all the students, all the staff, all the faculty. So for each of them, I'm just going to take their height and I'm going to plot it above the given height that they correspond to. So here I'm at 5'3", so maybe I'm there. So where would you be on this height chart? Okay, and if we did this enough, we'd get a whole distribution of our entire population. So that distribution would probably look something like this. Okay, so that's if we continue to fill in all of our population. So this highest part on such a curve or distribution this part here, that corresponds to the average of the entire population. Often we use a little mu, a Greek letter mu, to denote the average of a population. Okay, but taking data on an entire population is difficult and oftentimes not possible. So, how do we get around this? How do we find information about the population without sample or without collecting data on everyone? Well, what we do is we take a sample. So, I just take some of these people's data. Sample. And so we don't collect data on everyone, just a subset of the entire population. And with that, we're going to get a different distribution. Maybe our distribution looks like this instead. So maybe it'll be slightly smaller because we're going to use less people. And so we're down here. So now from this sample, I'm just going to fill it in to really emphasize the sample, the distribution of the sample data. We have a different mean. So the largest or the most common height for our sample data, often we denote as X bar. That's our sample mean. And I'll write that out because we're going to see that again, sample mean. So again, in this scenario, we don't know the green distribution. We don't know that information about the population because we're not able to get all of it. But we do know information about this smaller group, this sample. So now when we create a confidence interval, what we do is we create a range of values based on this sample data that's going to be used for us to predict where that population mean should be. So in this case, say our range of values goes from here to here. And what we'll see is when we create a confidence interval, we always have that sample mean in the middle. And then we're going to collect a certain amount on both sides. So it's symmetric here. So in this case, our confidence interval would start from maybe about 5.1 to 6.4. So from 5.1 feet to 6.4 feet, this is an example of an interval of heights. And we'll see specifically how to make a confidence or find a confidence interval of heights or of data from a sample. So then with this interval 5.1 to 6.4, why did we create it? What was its purpose? Well, it's created because it's a prediction of where to find the population's average. So a couple things to note here is that different samples are going to give you different confidence intervals. I'm going to make a note of that. Different samples create different confidence intervals. And I'm just going to write CI for confidence intervals. Another thing to note is that not every confidence interval is going to include or capture that population parameter. So the one that we created here, turns out it does. We can see that the mu, or the average of our population, does fall within our range. But it might have been that our sample was maybe all down here and that our sample didn't include that range. So that's where probability comes into our confidence interval. All right, so now we're going to get into the details of how we actually calculate a confidence interval. And here's where we're going to see where probability comes into the calculation. All right, so let's continue filling in these notes together. So for a calculation of a confidence interval, the probability with which a parameter should lie in the interval must be defined or given. So that probability is going to be given to you as a percentage. So you're going to always be asked, create a confidence interval with a certain percentage probability. So there are some common probabilities used to create confidence intervals, and you might have seen this in some examples in the news or maybe other classes you've taken. The most common probabilities that we look at are 95% and 99%. Now, when we actually get into the calculation of a confidence interval, we actually use a value associated to the probability called the z-value. The z-value you find according to the probability based on tables. And a quick side note, what the z-value corresponds to is from the normal distribution, centered at 0, standard deviation of 1, -1. The z-value corresponds to the number of standard deviations that catch that certain percentage of the data in a normal distribution. So 95%, the z-value would correspond to the endpoints here. So you don't need to know that for this video. In general, you can find these z-values by looking them up in a table. Google has this tables of all z-values that you need. You can just Google z-value for 95% probability. We're going to fill these values in a little bit after we see where that z-value comes in the calculation of a confidence interval. But for now, let's continue looking at our notes. So then after we create a confidence interval, how do we interpret the range that we create? And specifically, how do we interpret that probability involved in creating or defining a confidence interval? Well, here are two statements that are helpful for understanding an interpretation of a confidence interval. So most commonly we say, if a confidence interval of 95% is given, then we are 95% sure that the true parameter, so that's the value associated with the population, for the population lies within the interval. So again, if a confidence interval of 95% is given, then we are 95% sure that the true parameter value for the population lies within that interval. Okay, what does it mean that we are 95% sure of something happening? Well, here's interpretation 2, where we kind of make sense of that 95%. So that means if we were to collect 100 different samples and therefore create 100 different confidence intervals, 95 of them would create a confidence interval that did include the true population parameter. So 95% of the time that we do this work, that we create these intervals, we are going to actually capture that population parameter. Okay, so before we look at the formula, there are two requirements that we must have on our population and our data in order to use a formula to create a confidence interval. And here they are, the required conditions. So we have a requirement of our population, and that is the population data must be normally distributed. So we saw that in this example of heights that we sketched out up here. What does it mean for a population data to be normally distributed? It means that if we plotted all of the population data, it should look like a bell-shaped or normal distribution like this. Then we also have a requirement on the sample that we take. That sample must have at least 30 data values. Just taking too small of a sample will not give us enough of an accurate sample mean to create a confidence interval. All right, so with everything, all the background in place, we are ready for the formula to create a confidence interval for means specifically. So this formula that you're about to see will vary slightly based on if we're computing a confidence interval for a different parameter or statistic, meaning maybe a proportion of a population or a variance of a population. But for now, we'll stick with looking at a confidence interval for a mean. We're going to see an example after seeing this formula. So let's go through this formula. So CI, that's confidence interval, is equal to, so we begin with X bar, which is our sample mean, plus or minus Z, there's where that Z comes in, times sigma over square root of n. So let's unpack this notation. So we already saw what X bar is, but I'm going to write it again. So X bar is equal to the sample mean. That Z is our Z value. And that Z value we find in a table. And the Z value itself is determined by a percentage of probability. This is usually going to be given to you, this percentage. Sigma, that is the population standard deviation. If we don't know this value, which is often very common, then we can use the sample standard deviation. So sample standard deviation is okay. And then our final notation we have here is N. N is just the sample size that we've taken. Okay, so now you have all of the components that go into the calculation of a confidence interval. Now, a note that I want to say here. So we kept on saying about a confidence interval being a range of values, and here I've just given you one expression. Well, notice this symbol here. That means take the sum of these two values and take the difference. So you're going to get two values when you do that computation. And I want to make a note of that just because that point is very important, and many of us may have not seen this plus or minus symbol before. So I'm going to make a note. Plus or minus gives two values, a larger and a smaller value. So what do those values look like? Well, given our formula, they would look like X bar minus Z times sigma over root n, and X bar plus Z times sigma over root n. And here with this formula, we can see this range start to emerge. So let's consider a number line here. So what happens when we create this confidence interval is that our X bar is in the middle. Then we add a certain chunk of values, Z times sigma over n, over root n, excuse me, and then we subtract that same chunk. So when we create that confidence interval, again, we get this range of values, and that X bar, that sample mean, is in the center. And so that's where we saw here in our diagram looking at heights. Okay. So now let's finish off with looking at an example together. All right. So in this example, we are told that a random sample of 40 students at our school is collected. These students are asked how many hours outside of class they work each week. The mean number of hours worked per week for this sample was determined to be 17.5 hours. We know that for all students at our school, the standard deviation of hours worked is 5 hours. And we can assume that the distribution of hours worked per week is normally distributed. Determine a 95% confidence interval for the average hours worked per week of all students at our school. So let's unpack a little bit what we're asked to do and what information we're given. So we're told that we have 40 students in our sample, that the average or mean number of hours worked per week for this sample was 17.5 hours. We know the standard deviation of hours worked is 5. We know that we have a normal distribution of all population. And we're asked to compute a 95% confidence interval for the average hours worked per week of all students. So that's our end goal here, is to find this confidence interval to predict the average hours worked per week of our population. And we need to find an interval with 95% confidence. Okay, so let's go through the conditions to make sure that we can use our formula. So recall, those conditions are that the population must be normal. And yep, we are told that here, normally distributed. So check. We need our sample size to be bigger than 30, and we have 40, so that works, check. So now let's consider the information that we're given. And let's use the information we're given. Let's write it out using the notation that we see in our formula for the confidence interval calculation. So what are we given here? Well, 40 students are in our sample, so that's N. We're told that the average value for the sample is 17.5, so that's X bar. We know the standard deviation of hours worked is 5, so that's sigma. So all we need to know is our Z value. So what is our Z value for 95% confidence? Well, let's go ahead now and fill in the rest of that table of probabilities. So scroll back a couple of pages where we found that table of probabilities. So feel free to check this. Like I said, Google Z values for 95% probability, but you'll find that that Z value is 1.96. And just so our notes and table is complete, the Z value for 99% confidence interval is 2.576. Okay, so for us in our example, our Z will be 1.96. So let's scroll back to that example. The Z value here is 1.96. So then we can gather all this information we have. So I'm going to write given values. So we have X bar is equal to 17.5. We have Z is equal to 1.96. We have sigma equal to 5. And we have N equal to 40. So now we just need to plug these values into our confidence interval formula. So I'll write that formula out here again, just so we have it next to our work. So that confidence interval is going to be equal to X bar plus and minus Z times sigma over root N. So let's go ahead and set that up for ourselves. So for us, that would look like X bar is 17.5. We can do the addition first, plus 1.96, our Z, times sigma 5 over root N, which is 40. And I see I made a small typo here. This N is 40, not 50. The 5 snuck in. All right, so then our lower bound, our lower value would be 17.5 minus 1.96 times 5 over root 40. So what I'd like you to do is pause the video and go ahead and compute these two values on your own. And then when you have a solution, continue the video and compare your work. All right, let's compare together. So we should be getting, for when we subtract, 15.95 hours. And for the addition, we should be getting about 19.0495 hours. So we could even approximate a little more. This is about 16 hours. And our upper bound is about 19 hours. So here is our confidence interval, 16 to 19 hours. So how would we interpret that confidence interval or write a complete sentence of our solution? Well, we could say we are 95% confident that the average number of hours worked outside of class for all students is between 16 and 19 hours. So let's go ahead and write that down now. So we are 95% confident that the average number of hours worked by students at our school is between 16 and 19 hours. All right, nice job. Before we leave, one comment on this calculation. Perhaps you got something slightly different than me here. So one thing when you're entering this expression into your calculator, it's really important that you make sure you use what's called order of operations. So that means we want to do all of our division and multiplication before addition or subtraction. One way to make sure your calculator does that is to use parentheses around this multiplication here. If you enter in your calculator just straight across, so 17.5 minus 1.96, and then you do an enter or calculate equals, and then you multiply by this final fraction, your calculator is going to first subtract these and then multiply, which is not what we want to do. We want to first multiply and then subtract that from the 17.5. Same story here with the addition. All right, so now let's just summarize what we discussed here. So in summary, what did we learn? We learned that a confidence interval is a range of values in which we can find the population parameter with a certain probability. So we're not always going to find that population parameter in that range, but a certain percent of the time we will. In this lesson, we calculated a confidence interval for a population mean, but we can create a confidence interval for many statistical parameters. For example, a proportion of a sample, the variance of a population, etc. All right, thank you so much for watching.